work. I mean, I've never seen organizers bring so much life to their talks. And well, and for this and all the rest, I think we should. So thanks to you also for coming for this last talk. So I will. Is it everything okay? Yeah. All right. So today I will tell you about the Ising model and conformal field theory. Well, that topic is, from the physics viewpoint, maybe 30-year-old or something. So what I want to tell you about today is how mathematicians eventually ended up understanding this connection. So somehow, mathematics is about checking whether things are true or not, but it's also, and I think mostly, about bringing us from point A to point B in a very clear way, hopefully. And yeah, what I'm going to tell you is things that happened over the last 12 years, perhaps, and which gave us a fairly comprehensive way of understanding the connection between lattice models and conformal field theories, quantum field theories in general. Well, which can be proven, completely rigorous in cases like the Ising model, but generally give us a view on what's happening. And there are a number of surprises also for physicists, things that escaped, I think. Well, physicists, at the time they looked at these things, and well, hopefully everyone will learn something. So, well, this is just for notation, so I'm looking at the Ising model without magnetic field at this point. Just, this is just standard notation. I think you all know what I'm speaking about. So, what I'm going to focus on today is the 2D Ising model. So, the way we're going to understand it is, the Ising model we'll take it on the square grid for just concreteness. Can be generalized to other lattices. And when I mean what I mean by the Ising model on the square grid, I mean the Ising model on square grid approximations of continuous domains. So what you see here is a simulation of the Ising model, and I'm tuning the temperature. So as you probably know, there's a phase transition which makes us go from order to disorder. So in this picture, we have drawn plus spins in white and red, minus spins in red, and we have taken plus boundary conditions. All right. So as you probably know, also there's a phase transition at a critical value of beta. And one way to describe what's happening is in terms of such a picture. So you discretize a domain with a fine square grid of mesh size delta, and you take, say, plus boundary conditions, and you look at a spin in the bulk, and you ask what is its limit as the mesh size gets small as we look at the system from far away. So depending on whether you above or below the critical point, you will get positive magnetization or not. So this is quite classical. Well, below the critical point, you decay exponentially fast, and at the critical point, so here's already something that's not quite trivial. Well, you have a power law behavior, as you can expect, as was not proven until fairly recently. So, well, can we see this visually? Yes. So this is an Ising model on a square box, discretization of a square grid, and we ran a Monte Carlo simulation of the system, and we take the running averages of the spins, and if you run them for long enough, you see something that emerges, and something that looks a bit like complex analysis. So so it seems that there is maybe something interesting going on here. So this should be witnessed by the fact that so at critical temperature, the magnetization goes to 0, as you would expect from the fact that it's a continuous phase transition, like a power law, as you would expect. But the constant in front of this power law should actually be something interesting. Should be a geometric quantity. Should be predicted by conformal field theory. So This is, the one-point case of a theorem that we proved quite recently with Dimachalkak and Kostya-Dzurov about all the spin correlations of the critical Ising model in arbitrary domains. So if you take any domain, and fairly general boundary conditions as well. Well, for the sake of concreteness, I took plus boundary conditions, but you can have a certain level of explicitness for various boundary conditions. If you look at n locations in your domain and you look at the correlations, and you ask how do they behave as the mesh size goes to 0, what you get is that they decay like a power law naturally, like the number of points to the power n over delta to the power number of points over 8. And if you renormalize by that, you converge to continuous objects, which are the objects that conformal field theory has predicted about 20 years ago for bounded domains. So recently we were able to get very explicit values for these correlations in the half plane, and we were able to most importantly show that these correlations are conformally covariant. So if you can compute them in the half plane, say, you can compute them in any simply connected domain at least. Question? So why did I draw this picture? Just to give a very simple illustration of what these formulas mean. So the one-point function with plus boundary condition is just given by the so-called conformal radius to the power -1 over 8. So the conformal radius is a measure of the size of the domain as viewed from a point conformally. So it can be given in terms of Riemann mapping to a disk. It's quite easy to visualize. This picture of Escher for the disk, you can see the conformal radius is about the size of a fish at the point. Okay, and well, that's the one-point function with plus boundary conditions. For instance, the two-point function with plus boundary conditions is the product of the two one-point functions times the interaction term, which is 1 minus exponential of -2 times the hyperbolic distance between the points. Something that's quite easy to visualize as well. Here, it's just between 2 points is the number of fish, roughly, that you need. Well, in this picture, yes. It's an illustration of what this is on the disk. In general, it's a conformally invariant quantity, so on your favorite domain, you just map it conformally to the disk and you look at where the points landed. Critical. Yeah, maybe I went a bit fast. So somehow, what we are going to focus on, at least at the beginning of this talk, is the critical point. All right. So yeah, these things somehow, were among the great advances of physics in the 80s, 90s, and well, people like Bertrand worked on this for sure. Well, fairly recently, we were able really to go from the lattice model to the field theory to these formulas. So I'm going to start by telling you a little bit how we go from a lattice model to a formula like that, without going too much into the details, but just to give a flavor, a feeling of what's happening. They're just points, locations of the points. Yeah. In the half plane here. Well, this is the half plane. So you just, yeah. So this formula is actually probably quite deep. Somehow, I think it's something that's worth also looking at, trying to understand all the deep structures behind such a formula. But I just put it here so we get a sense that it's a fairly non-trivial, non-Gaussian, for sure, correlation. It's also fairly explicit. Yeah, so the AKs are points in a half plane, and so you get the product of the one-point functions times this interaction term, which is made of distances between the points and their mirror images. Okay. So I can also say something about the way this was conjectured. It's not very satisfactory in the sense that, well, from the framework of conformal field theory, which I'm going to talk a little bit about later, you get partial differential equations that these functions should satisfy as functions of the locations. But it's not clear that these partial differential equations have unique solutions even once you fix some asymptotics. And this formula was initially only obtained by extrapolation from 2 and 3 point functions, which can be obtained somehow with a clear methodology. The more point functions were not really obtained with any clearer methodology than extrapolating from the 2 and 3 point cases. Yes? No, I mean, in the half plane, no. I mean, in the full plane, for sure, there are ways, but you know, the usual way to solve this, for instance, in the full plane would be Coulomb gas, but it's a bit tricky with bounded domains. So no, I mean, somehow, yeah, these formulas were only obtained a bit later by Burkhardt than the main developments of CFT. So 92, I think, Burkhardt and Guillaume conjectured this formula, again, only on the basis of extrapolation, and well, and then checking consistency of these formulas. So anyway, let me just give a very quick overview on how we are going from the lattice model again to such formulas. We are not going immediately to the field theory. Comes in the second part of the talk. It's just to give a flavor. All right, so I'm not going to spend too much time on these details. Just again, to give a flavor. So, well, the language I'm going to use in the next slides to describe the model is just simply that of a loop model. So just think the low temperature expansion of the model. So you just look at the boundaries of spin clusters, and they form loops naturally if you have plus boundary conditions. And well, naturally you can express anything here in terms of these loops. It's not particularly surprising. The key tool to pass to the limit will be the use of fermions in a somehow novel way. So, you know, how do you go from random walk to Brownian motion, for instance, a central limit theorem? How do you go from, well, various models of, you know, on the lattice to their limits, usually central limit theorem. But here, there's no way you're going to be able to use directly a central limit theorem, of course, because it's not Gaussian. And maybe it's alpha stable, but it isn't. So you need really some kind of different techniques to approach that. And these techniques were popularized for statistical mechanics by Kenyon and Smirnov. And the idea is to use somehow the integrability of the model to get what, you know, in physicist language you would call lattice equations of motion. So, well, lattice versions of partial differential equations satisfied by correlation functions. Well, then you may hope that in the limit, these equations of motion converge to continuous equations of motion. And then maybe you will get continuous correlations. Or scaling correlation functions. Well, this is a little bit tricky as a step for mathematicians, because it's not because an equation converges that the solution to an equation converges, but well, that's still roughly the framework. What's a bit tricky here is that spins on the lattice or in the continuous don't satisfy obvious partial differential equations or equations of motions, and so you know, any naive approach is not going to work. So we need to introduce something that satisfies an equation of motion, and that we call a fermionic observable. In the language of physicists, it's a fairly simple object that can be described. Well, I could just write this. So psi tilde A psi of z. This is my function. So if you know what lattice fermions are. And so what is psi tilde? Psi tilde is just the sum of the left and right moving fermions, if you know. Okay. So, well, it's a fairly simple object. But thanks to the integrability of the model, this object satisfies something like lattice PDEs. So, well, here's the definition in terms of this language. But again, I just want to give a feel out of what's happening. So this So to understand what this object is, you just need to understand that it's a kind of correlation, well, where you, in addition to looking at points, you introduce a frustration in the model along a specific line. Well, anyway, so this is just pictures trying to explain a little bit how one can visualize the addition of a frustration line. Anyway, beyond the bare definition, what's important is that you have revealed the integrability of the model in a specific way that will scale very well. So as a function of its second parameter, z, this function is actually discrete holomorphic in the sense that it satisfies a lattice analog of Cauchy-Riemann equations. So you can really think of it as a discrete analog of holomorphic functions. Moreover, it's fairly simple from the analysis to find boundary conditions that this function that you introduce, this artificial function, satisfies. All right. Well, it's a bit less trivial to show that this uniquely characterizes your function, and in some sense, it tells you this data, the equation of motion, the PDE, and the boundary conditions tell you essentially everything. Well, what's important about this function, these artificial functions we introduced, is that when you evaluate it at a specific point, when you merge z with a point A, it gives us a non-trivial piece of data. And actually, it gives you the expected value of the product of two spins. So this is not quite spin correlations, arbitrary spin correlations. It looks more like a one-point function of the energy density, but okay, it's a first step. It tells you, okay, there is something about the model you can represent in terms of discrete complex analysis. So again, what did you do? You introduced some correlator. The integrability of the model yields lattice equations of motions at criticality only, the specific equations. And then you are able to phrase a certain quantity in terms of the unique solution to a lattice equation, lattice PDE. So then if you're optimistic or, well, good in analysis, you convince yourself that this lattice function converges to some continuous holomorphic function. Well, being continuous holomorphic with specific boundary conditions, well, you can actually compute it somehow explicitly. At least in a domain like the half-plane, you can compute it completely explicitly. And then you can ask yourself the question, okay, so if I want to recover something like that, I just need to merge z with A. And I do that. At first order, I get a pole, which reflects the fact that I should renormalize this quantity a little bit. And at next order, I get a number, which is exactly the properly renormalized limit of this correlator. So this was just for the energy density, and somehow it's an old story. Going to the spin correlations was much harder, but it's similar in flavor. So you have to tweak a little bit your correlator. You have basically to add spins in your correlator, in addition to this kind of observer. And now the spins, well, will interact somehow with this fermionic construction. And if you repeat the same kind of reasonings, you will get, as you collapse the point z with the other spins, you will get some information, some insight into what's happening. So you don't get directly anyway the spin correlations, but you're able to compare spin correlations at just slightly different locations. So bootstrapping from this information, well, which you can compute explicitly again, you're able to build more and more data, that you're able to pass more and more data to the scaling limit. And once you have passed enough data, you just try to put things together, and thanks to probabilistic inequalities, you can do that, and you can find explicitly all the correlations. So that's the way we found essentially all the correlations of the Ising model at criticality. And so it's a bit different from conformal field theory. Now I want to just tell you, yes, of course. All right.
Bootstrap is one of the central ideas behind this theory.
Yes.
So I was wondering, this complicated correlation function, could we have something simplified, some fusion of the fields?
Well, not obviously. I mean, somehow, well, in principle, bootstrap equations can be solved, but Like these specific equations, I mean, using the BPG formalism, the first conformal bootstrap, it's not clear to me how to obtain them. I mean, let's just take an example. No, but also to obtain them, I mean, again, they were obtained by extrapolation, which is not really a systematic approach, rather than bootstrap. I think it's, in general, very non-trivial. Like, for instance, I think, for sure, the 4-point function of 3 pods in a bounded domains are not known. But that's like an 8-point correlation in the full plane. For sure, there's no spin. I mean, spin correlations are not known. So somehow, I would say it's not so straightforward, because you would have to explain what works for Ising that fails for others, and that is a bit unclear. Maybe the methods we suggest allow you to get non-rigorously correlations for other models. So that's an interesting alley. But yeah, okay. So by bootstrap, I just mean help yourself aggregate what you have. I don't mean conformal bootstrap. Conformal bootstrap will be discussed just in a few minutes. Well, because it's a conference about random geometry and fractals, I think it's a good time to tell you something about random geometry and fractals. So using these results about correlations, you're able to gain more insight into the random fractals, the random geometry of the Ising model. So let me just tell you a few things about that. So you heard in a few talks, Scott, Sheffield, Bertrand, about, well, SLE. Yeah, so SLE is a collection of random planar curves that don't intersect themselves. The most natural conformally invariant random curves in the plane. Well, it's not surprising that the Ising model converging to things that are intrinsically conformally invariant, covariant, should have random curves that converge to such SLE curves. So we were able to prove, again, fairly complete results about what's happening here. So just to give you a flavor on how we go from things like that, spin correlations, just single quantities, I mean non-trivial but single quantities, to convergence of a whole process. How do you identify, these curves in the limit? So, okay, what are these curves? Well, you start with simple curves. I mean, simple in the sense non-complicated. So you can consider, a domain with the plus and minus boundary conditions. You put plus spins on half of the domain, minus spins on the other half. It spontaneously generates an interface separating plus and minus. So you can follow this interface, and you can ask, what does it converge to at criticality as delta goes to 0? Well, it converges to this SLE process with parameter kappa equals 3. So that was proven recently in a number of settings. So I just want to give you again a feel on how it's happening. So the first step is fairly technical. I think physicists would not be too interested in that. It's making sure that the curve is not crazy. Well, the curves can get quite crazy, as Scott illustrated in his talk. The curves we want should not be too crazy. They should not be space-filling curves or things like that. So you get an a priori control using, again, discrete holomorphic functions and stuff like that. But that's a fairly probabilistic step. The second step, which is more interesting to physicists, probably, is how you get knowing that your curve is not too crazy, from knowing that it's not too crazy to knowing precisely that it is an SLE3. The technique relies on something called a Martingale identification trick, which was popularized by Smirnov, but it's a tool in stochastic analysis. So it's a fairly powerful tool because it allows you to identify a whole curve from the knowledge of only certain quantities. So here, what I'm arguing is that from the knowledge of say the 1-point spin function in a plus-minus domain, you can bootstrap your information to get the law of the curve. So what's happening is that this curve has a special role with respect to something like a spin. It's actually discovering the Ising configuration as it grows. If you grow the curve from one point to the other, as it grows, it tells you more and more info about the value of a spin. So as a result, as the curve grows, you have something that, well, is like adding more and more info. And something like that is, well, you know, is the analog of a fair game. There's no reason why it should go on average more up than down, because you already try to average precisely in advance for what's happening. So on average, it's a conserved quantity from a physicist's point of view. And you get actually quite a lot of conserved quantities, because if you can compute things for an arbitrary position of the point, you have a 1 or 2 parameter family of conserved quantities. Basically, what you can argue then is the curve has not so many ways of wiggling, so many like tunes at which to wiggle randomly. So there's only one kappa that it can follow. So the curve can only look like one thing. If you want this to be a conserved quantity, and you have an explicit formula for what this is. So, well, basically that's how it goes. And then from the knowledge of one curve, with Kitola, we were able to extend this to free boundary condition, to an arc where you have free boundary conditions. We were able to catch basically all the loops which were discussed in at that talk, the CLE. So from the knowledge of just some information, you're able to get more and more information and put them together. I want to go quite fast, but just to give an idea, you know, the problem with these CLE loops, so the loops that arise when you take, say, plus boundary conditions, is that they don't touch the boundary, as you know, in the scaling limit. The macroscopic loops don't touch the boundary. So it's a bit hard to fish them with techniques like that, which are made to explore once you entering a domain with plus minus. So the first idea was to take free boundary conditions, which allow, you know, some arcs to touch the boundary. And using techniques like that, we were able to recover all the arcs. But then, you know, you may think free is a bit artificial. I mean, you want, say, plus to get this CLE. So how do you go around that? And the next idea was to couple the Ising model with this FK Ising model that you heard of in Jacobo's talk. And FK model has the good feature of having loops that touch the boundary. So it was also homework. We were able to understand with these FK loops and show that they converge to another variant of CLE where the loops touch the boundary. And so we were able to say, okay, this FK model, at least we have it under control. We understand its loops touch the boundary, and as a result, we can explore them using this basic SLE. Now the thing is that the FK Ising model and the Ising model are intimately coupled to each other. And if you know the outermost FK loops associated with an Ising model with plus boundary conditions, you also know that the Ising model inside the FK loops is an Ising model with free boundary conditions. So something like that. So we were able to basically find these a priori invisible loops. Here, you know, you don't see loops that touch the boundary, but they are there implicitly. They are the FK loops, so they touch the boundary. And your Ising loops touch the FK loops themselves. So in 2 steps, you're able to go in and fish the loops. So that's how we were able to get the convergence of, you know, all the Ising loops to CLE3. Yeah. Yes. Yeah, exactly. Well, so you have to first, you know, and very good question. So you take a complementary of the Ising, these FK loops, and you take the connected components of each of them, and you say the Ising, yeah, exactly. But that's a very good point. It's a very subtle point, because you may get a lot of dust that's that's nasty. Here it doesn't happen, but it's a fairly subtle matter. I mean, if you look in the end, it boils down to some Bessel process being not too crazy. So it's a bit, you know, you're right. It may have failed. It doesn't, but it may have failed. So it's not as easy as it sounds, indeed. So we get, you know, these are the Ising loops, and this is the CLE process. So here's a simulation of the CLE process made by David Wilson. It's a very nice website, cle3.org. I recommend you visit it. So this is made out of random walks, but you know, now we know that these 2 things are symptotically the same. So as an application, you get something about fractal geometry. So as probably predicted by Bertrand at some point, some time ago. The Ising spin interfaces, they have fractal dimension 11/8, and the spin clusters themselves, the macroscopic spin clusters, have a fractal dimension 187/96. It's also nice to, you can use this to make connections that are fairly simple with a Gaussian free field, which Scott spoke about. But okay. Now I'll go, yeah. Well, I mean, so there are several ways. I mean, and some ways are smarter than others. The way I'm going to speak about is not super smart now, but I'll tell you. So if you you can construct CLE3 from Brownian loop soups. So the idea is, that's the way it was simulated on this website, actually. So you throw a cloud of random walks or Brownian loops in the limit, and then you do some hypercorrelation on the clusters of these loops, and you get CLE. And the intensity of the loop soups you use actually corresponds to the central charge. So now if you take 2 copies of this and look at the Brownian loops you use, and you superimpose them, the Brownian loops, and you do percolation on the union of these Brownian loops, you get CLE4, level lines of the free field. So at the lattice level, what does it correspond to? If you take 2 independent copies of Ising model on the same graph, and you take the maximum of these 2 copies, and you trace the boundaries of the outermost loops of the maximum, and then you get CLE4. So it's a connection with the Gaussian free field, which is an example of bosonization. But of course, there are smarter ways to to connect to the free field, like the Dubéda's exact bosonization is maybe a bit more smarter, but that's at least simple enough. I can tell you about it. All right. So okay. So this is somehow what mathematicians love to do: prove that you go from point A to point B, you go from the Ising model to continuous formula for scaling correlations, to random processes, to random fractals. But somehow what I wanted to do then was to understand the very framework which led to the predictions that this was stimulated by. So how did the physicists understand the connection between quantum field theory and lattice models? So, well, it's a fairly complicated story, but I claim it's not as complicated as maybe mathematicians would have thought, or maybe physicists would think all the time, why can't mathematicians understand that? So I'll try to, pinpoint, a number of things that can be said in a bounded amount of time, and explain something that is, again, hopefully interesting to both mathematicians and physicists. So, all right. So don't look at the right-hand side. I just don't want to show you the left-hand side anymore. So the question, you can start by asking, if you're a mathematician, how do you really go from a lattice model to conformal field theory? So first, what is conformal field theory as a mathematical object? Well, some people have algebraic definitions which are not necessarily super useful to understand lattice models. So let's, fix a very clear objective without being too serious about it, because maybe there's more than the very objective. So let's ask the question: how do physicists go from a lattice model to exact formulas, such as the ones we saw, but not exactly that one, because they were not able to obtain it systematically, but maybe other kind of correlations. They were able to compute so many things. So how do you go from a lattice model to something exact with the reasoning of conformal field theory? Well, so the first insight is that the lattice model, you should extract some data from it, and what you should extract is correlations to study conformal field theory. So you should find fields, like operators that will scale to field theory operators. I want to focus here on local fields, so a bit not like the ones that Jacobo studied for percolation, more like spins, or maybe energy, the product to adjacent spins, so things like that. So yeah, imagine you have extracted some quantities. You don't need to prove it. You just assume that, okay, some things go to the limit. You have a collection of local fields. I'm going to clarify this next slide. But okay, you have local fields, a number of them, probably an infinite number of them. And among these local fields, there is one that's going to really help you. It's going to really make you able to go from basically nothing to everything. So that object is the stress energy tensor. So it's a special local field, one very distinguished local field, not the spin, not the energy, another one, which has a dual role. I mean, at the same time, it's a scaling field. At the same time, it plays the role of geometric modification. So if you're a mathematician, the way you want to understand this, I'm going to say a few things about it later, but it's really, okay, if you change a bit the metric of the model, the surface on which your model lives, if you change a bit this metric, how does your measure respond to it? You may expect a kind of change of measure. And change of measure is given by a random-Nicodim derivative. And the random-Nicodim derivative is nothing but a random variable. So somehow there should be some random object which tells you how the model is going to respond to geometric deformations. So this is a very non-trivial thing to make sense of, but you can believe that it exists if you're a physicist. And having such an object is very powerful because it allows you to translate geometric properties in terms of field correlation identities, also known as operator product expansions. So the conformal invariance is something that you either want to prove or assume. Well, it comes from the idea that you have a limit, which is a scaling limit, so a scale invariant. By universality, you assume it's rotation invariant. And by your locality, you promote the scale rotation and obvious translation invariance to conformal invariance. So if you want to promote conformal invariance to something in terms of this stress energy tensor, if you want to say conformal invariance means something for geometric deformations, what it means is that this stress tensor becomes a holomorphic field. What do I mean by holomorphic field for mathematicians? I don't mean a random holomorphic function, although a random holomorphic function would be a holomorphic field in that sense. The converse is not true. A holomorphic field is a field which typically will look super rough, but its correlations are holomorphic functions. So on average, it's holomorphic, not at the realization level on average, all right? So, okay, once you have this holomorphic guy, what you can do is you can use it to probe how other fields are going to react to changes of metric. So if you have a field F, what you can do is you can play a game where the stress tensor is going to dance around the field. So you have your field here. So imagine you observe just a spin, and now you have this stress tensor, which is a field living at a point, and now it's going to dance around that field in a small contour, and you're going to weight that by some holomorphic monomial. And okay, what you're going to get in correlations will not depend on the choice of the contour because the guy was holomorphic integrate with respect to the position of this guy, which dances around. And what's very powerful is from the operatorial identities you get as a consequence of the assumed conformal invariance, you can prove that these operators satisfy the so-called Veeraraju relation, so they form a representation of the Veeraraju algebra. Once you're there, you need to classify a little bit what kind of Veeraraju representations you're going to find in your field theory. Now you find tons of them because for every field you act on it by the Veeraraju algebra, you get a Veeraraju representation. So what kind of things do we have? So using reflection positivity for models like the Ising model, you're able to really narrow down the kind of representations you have, namely the unitary representations. Then you can try to ask what are the unitary representations. So here you need some extra input, which is a little bit non-trivial to get. Maybe you can give me some feedback on that, because I haven't found really anywhere a completely satisfactory explanation. So if the central charge is less than 1, why should it be? Well, we can ask. But if the central charge is less than 1, then you can classify all these representations very simply. So now why is less than 1 something you want? I think the best explanation is to this connection with SLE, CLE. But okay, if you have explanations why natural, I mean the simplest, the most beautiful lattice models are C less than 1, I'm always happy to hear. But okay, anyway. So once you have these representations, then you get that they form a very classified family, which allow you to classify the L0 eigenvalues which are the ways you react to scalings, which are the allowed critical exponents. And you have then, only some representations that are allowed, so you can bring back any degeneracy that you will find from here to stress tensor quantities, which are geometric, so you will get geometric info, like PDEs. All right, so then you get your exact formulas by your favorite method, either guessing or using heuristics like Coulomb gas. All right, anyway, so what I want to talk about right now is not too many things because we don't have too much time. I want to tell you something that I think physicists would think is wrong, but it turns out to be true. So, so it's something about the Veeraraju algebra precisely. All right, so this picture, this heuristic picture, if you want to make it rigorous, maybe you should start here. What are these local fields? So I propose something as a definition of a local field. Well, it's the simplest, most naive definition you could come up with. It's, a local field is going to be something like the spin field, something like the energy field, the product of two adjacent spins, maybe the product of three adjacent spins, maybe a polynomial in a finite number of spins. Basically anything of this type, any polynomial function of a finite number of spins of the model applied in a translation invariant manner. So any recipe that you can apply to a field, you could take the derivative, so take the difference of value here minus the value at the neighbor, etc. Any polynomial should be, in the limit, a lattice local field, if it's not 0. All right. So I called F on the right-hand side here. Yes. Sorry?
Lattice symmetry transformation.
Mm-hmm.
How it's looked like. In order to understand transformal algebra and lattice, better first to understand conformal transformation.
On the lattice? Well, I don't think it's possible. So, well, it's certainly not easy, and probably, I don't have a good explanation of what they look like on the. Well, you can discretize conformal transformations by circle packings, like Scott Sheffield explained. But well, I think there's a better way. Yeah, that's my point. So, okay. So let's define the space of all the fields that I defined this way. All the polynomial recipes applied to a lattice model in a local fashion, and modeled by all the null fields. So all fields that, yes, fine, yes. Modeled by all the null fields, all the fields that are by 0 when taken correlation against, other fields. So that space is a space where I claim that there is a representation of the Veeraraju algebra at the lattice level. Exactly. Somehow there was a question initially raised by Itoyama and Thacker in 1989. So they asked, okay, so you can probably go from integrability on the blackboard here to well, conformal field theory somehow. At least integrable models like Ising have a CFT behind them. CFT is a very powerful symmetry also, I mean the Veeraraju algebra. This is a powerful symmetry as well, maybe Young-Baxter or discrete complex analysis. So probably there is a connection between both, at least asymptotically you can probably relate these things. But, are these structures exactly related? And you would think of after all these years that if there was a Veeraraju symmetry in the Ising model, you would know it. But actually, no, it was not known. And so it's a bit challenging to find, but I can tell you a few things about it. So the first thing is that you need to be very optimistic. So you need to think that everything can be discretized in a completely exact fashion. You need to maybe first believe, like I did initially, or maybe this formula like that, I can really totally make sense of it at the lattice level. Also, I already proposed what a lattice field is. Maybe I find a lattice stress tensor. Maybe I find a lattice analog of this. Maybe I find a lattice analog of a contour integral. And maybe everything works. No, it doesn't. Well, why doesn't it work? Because I did not find, I never found, and I think we will never find a discrete holomorphic stress tensor. Well, maybe that was just too much to ask. Okay. Well, something that we were able to do first was to construct something like that, discrete monomials, discrete holomorphic monomials, discrete contour integrals we were able to do, getting discrete integration by parts we were able to do, but we were not able to find this guy. However, we were able to realize that the stress tensor for models like the Ising model, but not only, for Gaussian free field or for more complicated model like affine catch Moody models is almost always a quadratic function of simpler fields. In the case of the Ising model, it's a quadratic in the fermion. So the idea is the stress tensor for Ising is something like psi d psi. This guy is discrete holomorphic. Product of two guys that are discrete holomorphic is not necessarily. The lattice level is very unforgiving. You cannot take products of things that are discrete holomorphic and expect them to be discrete holomorphic. However, if you look at the modes of this guy, there will be convolutions of modes of this guy and modes of this guy. So if you're really optimistic, you can think, okay, I can construct my Veeraraju algebra from the so-called Sugawara construction in string theory, which is really saying exactly this. You can construct the ln operators from the modes of the psi operator. Well, so if you're optimistic, and we were, everything works. So you need to be a bit careful, split amongst spin even, spin odd fields. It will split naturally in terms of what's called the Raman sector or the Neveu-Schwarz sector. And everything works out beautifully in the end of the day. You really connect the lattice integrability in form of discrete complex analysis to the full Veeraraju algebra with central charge 1/2. Same works for Gaussian free field and probably for affine catch Moody models. All right, so I had many more things to tell you about how you can discretize the stress energy tensor, but I think what I'm going to finish is by saying thank you. Yes.